So, have you ever wondered how to go about the process of prototyping a circuit board? Well, today in the lab we required an amplifier, and the circuit is already designed, so we need to build it and test it. So that's what we're doing. Now let's do it. We will be using an instrumentation amplifier with a feedback network which includes an op-amp, and both chips are made by Texas Instruments and can be bought from RS Components. This is the circuit we are going to be making. It has a variable gain depending on the value of RG and should filter out all DC signals. Okay, so the instrumentation amplifier we're using today is the INA111 from Texas Instruments, which should be available from most component stockists. And this particular amplifier will be built using a feedback filter to get rid of any DC components from the input signal. So the first thing I'm going to do is power the chip, and it takes a plus and minus 15 volts, and with all amplifiers of this nature the power supply levels affect the maximum signal output level. So next I'm going to connect the two inputs. So this amplifier is a differential amplifier, which means it will amplify the difference between the two inputs. One is the inverting input and the other non-inverting. I also need an output. At this point I'm simply working from the pin map from the data sheet, which tells me what wires have to be connected to where. So now I need a feedback network that links in with the op-amp, the second chip I've got. This consists of a resistor and a capacitor, which in conjunction with the feedback op-amp removes that DC component from the system. This circuit is taken directly from the suggested circuits in the datasheet. Okay, so this circuit also has parasitic leakage that goes through the inputs, and this current needs an outlet for things to work reliably. So we can get rid of this DC current by putting 1 megaohm resistors from each input to ground. Because the resistance is large, this shouldn't affect the input signal too much, but it should allow any persistent current to flow down to ground. I'm also putting a couple of capacitors on the power lines to smooth out any incoming power. So just putting the finishing touches on this op-amp circuit, and the system's complete. So now down to testing. So I'm connecting the test signal from a sine wave generator to the non-inverting input and the inverting input down to ground. So all references from electrodes are being connected to the ground of the system. So the output's been connected, and now we need power. I'm using simple benchtop power supply and supplying it with minus 7.5, 0 and 7.5 to test the system. The power supply readout happens to be broken on this power supply, and I wouldn't normally recommend using broken power supplies. So the oscilloscope has been powered up and connected to the output. You can see that on screen. And now we're connecting the resistor that spans from pin 1 to pin 8 on the instrumentation amplifier, which controls the gain. Now the gain of this amplifier at the moment is 1, and the output closely matches the input, but when you put the resistor in, it dramatically increases the gain, and you can see the output is now significantly larger than the input, with a gain of around 30. So once we're done with the breadboard prototyping, we want to make the system more permanent, and we'll do this by soldering it onto Veriboard or strip board. So first I need to cut it to size, and I want it to be fairly small, so we'll be limited by the amount of real estate I've got to play with. Now I always begin by soldering the lowest profile components, which are the chips in this case, and I'm using the chip carriers just in case the chips break and I need to replace them. Now I'd like to point out two things. One is that this soldering iron is way too big for the job at hand, and two, that when messing with chips it's usually good practice to observe anti-static techniques. So now I'm going to cut the interconnects between the pins to make sure there's no short circuits between each side of the chip, because if there is and I plug them in and power it up, it'll probably lead to bad things. Put the chips in. So when you're soldering, what you need to do is make sure that all three metals, the copper of the board, the steel of the component, and the solder are all hot enough to melt the solder. If you do this, the solder should stick evenly to where you want it, rather than clinging obstructuously to the end of the soldering iron. So now I'm going to do the wires as before. and being careful to map where the tracks go and where they need to go. And I always trim spurs from the components as I go along. I'm also making sure that no components are connected to each other via copper if I don't want them to be. Add the capacitors and resistors in place. The capacitors on the power supply, one goes from ground to V plus and one was from ground to V minus to try and smooth out both the positive and negative. So now I want to be able to connect the circuit to other equipment, so I'm adding some connectors. And the idea is to have this circuit in a sexy box at the end, and these will offer a sturdy connection to almost anything I want. They are simple 4mm screw-on assemblies which can be soldered to your wires. So just checking it still works. Yep. So this is the box the old amplifier was in, and these are the lame-ass connectors that I purchased from eBay. I would recommend buying some higher end components from someone like Farnell or RS Components personally. So now we put our amplifier into its pretty box. I drilled 6 4mm holes in total, 3 for power, 2 for input and 1 for output. So let's see if the final thing works. I can connect these up with just wires now. However, for the inputs and outputs, shielded coax cable will be needed in the end for our applications. Again, I am connecting the inverting input to the ground of the system, and all measurements will be taken relative to this. Power it on. And that's a nice sign. So this one is the amplified signal, this one's the original signal. This is it's a working amplifier, which is fantastic. Oh yeah. Okay, so here we have a fully functional amplifier, and thank you very much for watching this video.